Hello and welcome to our talk here today, Continuous Delivery and Resource Health for SpinKube and WASM applications with ArgoCD. I'm Luke Phillips, a staff software engineer for the New York Times.
And I'm Radu. I'm the founder and CTO of Fermyon.
And today we'll explore how these technologies continue to create a powerful delivery platform together, how we merge together WebAssembly and ArgoCD for the next generation of cloud-native applications. We're excited to share practical insights and demonstrate to you how you can apply these in your own environments. Some of the things we'll be talking about today, so for our agenda, kind of talking about some continuous delivery, we'll get into what is WebAssembly. We'll start showing WebAssembly with ArgoCD, ArgoCD resource health checks and observability of the WebAssembly applications, and then some other real-world applications and best practices. So given that this is ArgoCon, I trust that you are all experts at continuous delivery, though let us go over a few principles just to make sure. Continuous delivery has grown significantly since its inception. While the core principles remain, versioning everything, automate extensively, deploy frequently, the technologies we apply these principles to have changed dramatically. Today, we're managing deployments across diverse environments, from data centers to edge locations, multiple runtime environments. There's a new frontier as well in WebAssembly, and applying CD principles to this technology creates unique challenges and opportunities. Now let's have Radu introduce WebAssembly.
Hello again. I think one of the two key takeaways from this talk is why should you care about WebAssembly? This talk is about doing continuous delivery for WebAssembly workloads, and I'd like to take a couple of minutes to just introduce the concept of WebAssembly, why is it used for, why is it an exciting thing, and whether you should or shouldn't care about it. So at its core, you can think about WebAssembly as a compilation target. In your CI, you probably target like Linux x86 or macOS ARM64. WebAssembly is just another one of those. It's a portable compilation target, which means you just compile your Go or Rust or JavaScript or some other programming language to this new portable format. And if you pay attention to the name WebAssembly, it started in the web browsers, like it originally came out of people trying to run Photoshop and Google Earth and AutoCAD and all of these native applications, and they wanted to run those in the browser. And so what they needed really was this intermediate format that at its core needed to be sandbox isolated, which means any code that runs within a WebAssembly runtime does not have access to anything outside of its sandbox and does not have access to any API unless the guest explicitly grants it access to. Similarly, it needed to be cross-platform and cross-architecture. Going back to the previous point, once you've compiled the WebAssembly component, you can now deploy that to your Linux server, to your macOS server, to a RISC-V CPU or ARM or Intel. Similarly, because you just compile source code and it does not bundle anything else, it can be orders of magnitude smaller compared to some container images, which means much fewer bytes to fetch over the network. And because of its fast startup, it means putting those two together, you can start from scratch and scale up WebAssembly workloads significantly faster. And finally, it has support for a wide range of programming languages. I was at a WebAssembly conference last week, and Oracle demoed on stage GraalVM compiled to WebAssembly. So anything from Java to .NET to Rust to a whole bunch of programming languages can compile native to WebAssembly. And if you take away one thing from the next couple of minutes is WebAssembly is not going to replace containers. Containers are going to be there until the dying heat of the universe, but there are a bunch of workloads where WebAssembly, because of its runtime profile and because of these properties, running WebAssembly instead of native containers or native executables is much more advantageous because of those things. And if you can think about serverless functions and plugin systems and IoT and all the scenarios where you may not need a full container with a full Linux file system, WebAssembly makes a ton of sense. And I'm one of the maintainers of the newly CNCF Spin project. And Spin really takes the concept of WebAssembly and building WebAssembly functions and applies this sort of streamlined developer experience to all of it. So I'm gonna, in a minute, walk you through how you can create a new WebAssembly application using Spin, and then run that on top of Kubernetes, and then hand it off to Luke to essentially take that application and apply continuous delivery and continuous delivery principles using Argo, and basically show you how you can continue to use your existing patterns, your existing systems, and your existing tools to not only deploy your existing containers, but apply the same principles to WebAssembly workloads as well. So as I mentioned, at its core, Spin is, can you see my screen? Yeah. So at its core, and by the way, Spin, as I mentioned, fully open source. You can find in the Spin framework, GitHub org, similarly to the Spin operator project. At its core is just the CLI that helps you start your new application. So in this case, I'm going to do Spin new. I'm going to choose Rust because I'm a pretty big Rust fan, but there's templates for .NET and hopefully soon Java and Go and other languages. And basically, that just creates two things for me. It creates a tiny manifest that describes what my application is and what WebAssembly thing to execute. And then, depending on your programming language, just a function. So as I mentioned, WebAssembly is a great fit for serverless functions, and that's what the Spin project is particular about. It's just a function. If this is just an HTTP request, returns an HTTP response, and in the process, you can do anything that compiles to WebAssembly, or you can use the WebAssembly ecosystem. So if you can imagine, if this was a JavaScript function, this would have been fetch, and similarly for other languages. Spin build takes the source code, uses your underlying compiler to generate the WebAssembly component, and then I can do spin up, and I now have a full serverless application running locally with WebAssembly. What do I do now? I've built the application, I've presumably pushed it to my GitHub, GitLab, Git repo. Now my Git infrastructure can just do spin registry push. This is compatible with your existing container registries. In this case, I'm using GHCR, the GitHub Container Registry. We're using Harbor in production. We've used DCR. We've used Azure's Container Registry and Google's. This is compatible with existing registries. And now I can reference that application from a systemd unit, or from a Kubernetes cluster, or from a Nomad cluster. In this case, I'm going to do SpinKube scaffold, which it will generate a manifest that is compatible with the SpinKube project. And this is very quickly what I would like to introduce another part of the Spin project, which is the SpinKube platform, which you can think of as a way to take the application that I just built and efficiently deploy that on your existing Kubernetes clusters. It is part of the CNCF project called Spin. And it has three big parts. It has an operator with a CRD. I'm sure you know all about those. It has a runtime class manager. Behind the scenes, this uses containerd infrastructure to define a different runtime class. And then we collaborate quite closely with the containerd project. So the whole point here is, instead of executing containers, you execute WebAssembly components. But to the outside world and to the rest of Kubernetes, everything else seems as if it's a pod. So the reason the SpinKube project exists is to be able to interoperate with a lot of the cloud-native ecosystem and integrate with tools like ArgoCD and horizontal pod autoscalers and Kada and Istio and a lot of the tools that we're here this week to talk about, but efficiently execute those at the runtime level and execute WebAssembly instead of containers, and get all the benefits that we talked about WebAssembly. So last thing that I'll show you here is I'm running SpinKube scaffold, and I'm pointing to that registry reference that I just showed you. And I now have a CRD that points to my application that I push to the registry. There are tons of examples on how you can mount volumes and secrets and do a lot of things you may be already familiar with. I can do a kube control apply. And I now have a Spin application with 2 replicas in my cluster. If you're curious what that looks like behind the scenes, these are 2 pods for my 2 replicas. But again, they're not running containers. They're running WebAssembly components behind the scenes. And if you're interested in talking about the underlyings of how SpinKube is built and how it interacts with Containerd, I'd love to talk about that. I want to hand it off to Luke to take this application that I just defined and walk that through the entire ArgoCD process.
Never do at a demo is try to switch machines live during your talk. Let's see what happens. That worked. Amazing. We're going to get to the demo here in just a second. We're going to give you some screenshots just in case the demo doesn't work here. But for this environment, thank you, Radu, for introducing WebAssembly and how you kind of get to the point of WebAssembly on Kubernetes. So we're going to have a Git repository that both is managing the SpinKube operator manifest as well as our WebAssembly application. And I'll show you how ArgoCD not only bootstraps this environment, but also gets the application running and then starts observing the application. So, once we have the application up and running, or once we have Argo bootstrapping a SpinKube cluster, this is kind of some of the high-level steps of what you're going to go through where in your cluster, this is an example of a few Argo applications, sync waves in the right order of things, where you need cert manager, then you get KWASM, shim. I don't know, Radu, why is KWASM there? But that's it. Yeah, it's part of getting everything you need for WebAssembly there. Then SpinKube, the operator, there's all charts for that. You deploy those things into your cluster, and you have a WebAssembly ready cluster. Then next you'll deploy your Spin application. So this is just a standard Argo application referencing here is just a source of a file or a folder. And so nothing special about the Argo app itself. I just have the sync wave as the last in my demo. But beyond that, you have the YAML that is the Spin app itself. Again, just very simple. It's the API version. Pay attention to that core SpinKube dev, and that it's a SpinKube app type, and that you're just deploying the Spin image, number of replicas, and tying back to the executor type. And so the flow of everything, once you have everything up and running, you have ArgoCD managing calls to Kubernetes. And as you make changes to your Git repo, those changes, ArgoCD will continuously sync that, tell the SpinKube operator that you have a new image, and the SpinKube operator knows how to pull the Spin registry, the WASM registry of those kind of things. Let me see what happens. Can I demo? All right. So you have Argo running, all the things it took for me to get Argo running, as far as all the various components. But finally, we have a Spin application. And what's great about this, we have the Spin app. It's deployed. You can see everything is great as far as healthy and synced, right? Isn't that great when you deploy a new CRD into your ecosystem and the CRD Argo reports as healthy, no matter what the status of any of the pods are. So obviously, if Argo says healthy, but you see something not performing well, what's the situation here? Well, we need to teach Argo how to be aware of the resources for every new CRD. You might have seen the keynote earlier this morning where I think they talked about 83 new health checks committed into the ArgoCD project. If you have a CRD, if you're developing one that's public, please commit it into Argo. Let me continue here. Why do you want to commit those health checks? As even posted in a CNCF blog post, that Argo is considered one of the top 3 observability tools. Its UI shows application health and sync status at a glance, letting developers troubleshoot without any kubectl access. You have notification integration to a variety of endpoints where you can then do Slack automations or alerts, anything like that, as well as view logs and events and everything like that, do creative actions or creative fixes in there. So how do you add this health check into ArgoCD. If you check out the documents, there's a great guide. There's both a kind of how you add custom health checks into your live ArgoCD, or how do you add these health checks into the core of ArgoCD itself, so everyone can access or be able to take advantage of what you've developed. A health check itself is pretty standard as far as being defined or defined via a Lua script. Resource health assessments examine each deployed resource and to determine if it's functioning correctly for all the standard Kubernetes resources, as well as many various public CRDs. Argo has built-in logic for the health determination. Custom resources like our Spin application need to extend ArgoCD to further understand that. Getting into details, how do you add this custom health check ideally, you want to properly monitor your CRDs. For us, a SpinKube application. We do this via Lua. Everyone's favorite hidden little script in applications is Lua scripts. A Lua script will examine the status fields of our custom resource and determine if the application is healthy, progressing, or degraded. And this will then enable ArgoCD to reflect on the WebAssembly application's overall health, providing warnings and notifications. Here's an example of how you might do this. Using the community health chart Helm chart makes this much easier. You can load this health check into your ArgoCD environment, into the ArgoCD configuration config map, as you can kind of see here under config CM, and then you specify your resource customization. Simply add your resource customization into the defining or describing your CRD. And once your testing is succeeded locally, say like loading this path, you can then commit the change into ArgoCD itself, and you too can be a committer to ArgoCD. This is an example of the health check that I've created. I've actually my example is a little more complex than this, but simply you have this health check object, and it has both a status and message field. You parse your CRD and decide what to populate for statuses and health message, and then you simply return that back in the script. And this is the open pull request that we have regarding SpinKube. So today, SpinKube, well, as soon as one of you actually out there in the audience approves a pull request, SpinKube will be available in ArgoCD as a viable health check. Let's see if we can try that out ourselves. In my local cluster, I have this pull request. If I just go ahead and merge in this change, risky live demo, merge in. So I have a health request, or a resource health check here. Show you what it looked like. While that's going, we'll go back to Argo. We'll make sure Argo goes and loads the new one. Code is out there. This is also what the code looks like here. This is our health check. A more complex version of that. We'll see if Argo picks it up in time. Oh no, I broke something. So pretending that the demo worked all the way through, this health check would then change to failed, and Argo would start being aware of it. But for the sake of the demo, we're not going to go debug that. Or for the sake of the presentation, we're not going to debug that. So assuming you have the health check working, what are the benefits of having Argo monitoring your CRD, making your CRD aware in ArgoCD? The ArgoCD and custom health checks provide significant observability benefits. Operators get that single interface for monitoring both the deployment status and application health. Developers can easily check if their latest changes were successfully deployed and are running correctly. The UI provides that quick access to logs and events for troubleshooting, and ArgoCD's notification system that can integrate to so many things can alert teams to health changes and complete the feedback loop that bridges the gap between code changes and production deployments. Some best practices based off some of our experiences with WebAssembly deployments. We've developed, making sure, like Radu was saying, that you're using an OCI-compatible registry for everything. Always explicitly version your modules, much like you've seen in continuous delivery best practices all around. Implement comprehensive health checks, both with ArgoCD and in your infrastructure. Allow yourself to monitor, and as well as you get into the rest of Argo, you can also dive into then progressive delivery approaches as well. To wrap up, we've seen WebAssembly is enabling new deployment models for cloud-native applications. ArgoCD provides the GitOps foundations for managing these deployments declaratively and consistently. Custom health checks enable proper observability, closing the feedback loop essentially for continuous delivery. And please, again, contribute your own custom health checks into ArgoCD. Links and references for everything we talked about today. We encourage you to explore this technology further. You can find the source code for SpinKube, as well as be able to try it out yourself, as well as everything in the demo. The demo should work if you try it out yourself as well. And you can reach out to us and the rest of the community in ArgoCD and SpinKube Slack channels. And if you want to reach out or find any of us, are online, but otherwise, thank you very much.